Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to talk about magnetism. We're going to talk all about different types of magnets, what makes something magnetic, as well as the behavior of magnets when we bring them close together. So we're going to recap what we understand of non-contact forces. We're then going to look at what are magnets, what substances are magnetic, magnetic fields and the concepts around attraction and repulsion as magnets are brought close together, and looking at the Earth as one giant magnet with its own magnetic field. So firstly, we're going to recap what we understand about non-contact forces. Now, if this concept is unfamiliar to you, then it might be useful to check out one of my previous videos, Types of Forces, where we go into the difference between contact and non-contact forces in more detail. But so, assuming that you know something about this already, we can recognize and remember that non-contact forces are those that can be applied without any contact between two objects. That is, the force can exist at a distance, rather than purely because the objects are touching. Now, there's three main non-contact forces that we are familiar with. The first one, which is the focus of this video, is magnetism. But aside from that, we also have gravity, that is the gravitational force, and also what's called the electrostatic force, or more commonly known as static electricity. You can see with the balloon picking up the pieces of paper and our old friend the Van de Graaff generator in the bottom corner. Okay, so all of these are non-contact forces. That is, they exist and they act at a distance. The objects don't need to be touching in order for there to be an effect. But so we're going to focus more particularly on what this magnetic force involves. But firstly, let's think about what are magnets. Well, essentially, a magnet is an object that's made of a material that has two magnetic poles. Okay, that is, these two opposite ends that have this magnetic behavior. We call one north and the other south. Now, if you know anything about compasses or things like that, you can understand why we would use these terms north and south to refer to magnets, because it relates to our very beginnings of this understanding of magnetism and thinking about the Earth and thinking about the direction of north and south in that context. But you can see we have some different types of magnets here on the screen. We've got a bar magnet, which is just kind of a rectangular shape. We've got a U-shaped magnet, and we've got some more sophisticated, what's called rare earth magnets, which are much stronger in their magnetic force than their typical bar magnets. But we also experience magnets in all sorts of everyday contexts, with our fridge, and other sorts of bits and pieces that we might encounter. But what substances are magnetic? Well, there's three main metals that we wanted to think about in relation to magnets. That we have iron, which has the chemical symbol of Fe, shown on the left-hand side. We've got nickel, and we've got cobalt. So iron, nickel, and cobalt are the three main metals which show this magnetic property. Now, other metals can be encouraged to have some temporary magnetic properties, but these metals, when they're set up as magnets, are called permanent magnets because it's always on. This magnetic force is always being applied. Whereas magnets that are only magnetic for some of the time are referred to as temporary magnets, as the name might suggest. That this idea that it doesn't last forever, or it only exists under certain circumstances. Okay, so electromagnets would qualify as what we call temporary magnets because they use electricity to switch the magnetic forces on and off. And we're going to look at electromagnets in a bit more detail into the future. But so I want to focus now on this concept of the magnetic field. So remember that a field is the area around an object in which a non-contact force can act or have an effect. Okay, and so we're seeing, in particular, focusing on the magnet, it's the area around a magnet in which it can have an effect on other metallic objects. Okay, so magnets don't affect non-metal objects, they only affect these certain metals, and also not all metals. A piece of aluminium won't be affected under most circumstances. Okay, so this area around the magnet is where this effect is going to be felt. We draw what we call field lines, which illustrate this magnetic field. These lines you can see on this image here, they have arrows written on them that show the direction of the force within the field. And if you trace these arrows, you can see they go from the North Pole to the South Pole. Now, even though these lines are kind of cut off towards the top and bottom of this image, we can extend them beyond and look at this in terms of these loops that go around both sides of the magnet. But the force traveling from the North to the South Pole, but also in three dimensions. we often would draw it as a 2D pattern, but it would exist all the way around that magnet in 3 dimensions as well. Okay, so this is the area of the magnet where it's going to have an effect. And speaking of that effect, what we notice some curious behaviors when we bring magnets together. That if we take a north pole of one magnet and bring it close to the south pole of another magnet, we see that they pull towards each other. We call this attraction. And we recognize that opposite poles attract. The reason that they attract is that we can see that their field lines, these lines showing that magnetic force, are in alignment. That going from north to south means that then these two magnets are going to pull towards one another. And we can see that also in the photo shown just to the right here, which uses iron filings to visualize these field lines, and seeing this connection and attraction between the north pole of one side and the south pole of the other. But if we bring the same poles together, so north and north, or south and south, we can see that those field lines don't line up in this situation, that they're going in opposite directions. And so when we have like poles that go together, they repel. Repulsion, which is the noun for this, is this idea where they're pushing away from each other because the field lines are facing in the wrong direction. We can see that in this photo to the right as well. We can see that there's almost this gap between these two north poles where there is no attraction, that the iron filings are being pushed away because these field lines are going in the wrong directions relative to one another. And so now let's think about this idea of the Earth as a magnet. So the Earth essentially acts as a massive bar magnet because there is iron present inside the layers inside the Earth. And so it generates this magnetic field that acts all the way through the Earth. And what we identify is that the field lines go from our geographic South Pole up to the geographic North Pole, which actually suggests that, contrary to what we might believe because of their names, that actually the North Pole of the Earth, geographically, is a magnetic South Pole. And that at the South Pole, geographically, is a magnetic North Pole, which is why compasses respond the way that they do, that the North Pole of a compass points towards the geographic North Pole, and vice versa. Okay, because inside the Earth, it's actually backwards. I know it's a bit strange to understand or to think about it in that way, but we can see this behavior exists, and we can trace these field lines. And for us as human beings, we're not the only ones that experience or have knowledge of this concept of the magnetic field of the Earth, that lots of different animals use it for navigation, that there's different kind of sensors that they have inside their brains that allow them to respond to the magnetic field in order to be able to get where they need to go without a map, or without being able to, to see their course otherwise. The other thing that you can notice here is that the geographic North Pole and the magnetic North Pole, and vice versa at the bottom, they don't line up. That there is a distance between these two things based on exactly what's happening inside the Earth and how it's generating this magnetic field, is that those two things are a certain distance apart, and that distance is changing ever so slightly over time as the magnetic field of the Earth gradually shifts. Okay, but so the Earth acts as a giant magnet, generates a magnetic field that we can visualize, and helps us to understand a lot of the behavior of how magnets work in other circumstances. Okay, so we've recapped what we understand about non-contact forces, seeing that magnetism is only one of the non-contact forces that exist in the universe, gravity and electrostatic forces being the other two that we mainly focus on. That we looked at what are magnets and what substances are magnetic and respond to magnets in this way, looking at also the difference between permanent and temporary magnets, and looking at this idea that of a magnetic field and seeing attraction and repulsion between opposite and like poles, that opposites attract whereas like poles repel, and seeing that the Earth itself is a giant bar magnet with its own magnetic field. Alright, thanks very much for watching. Don't forget to like and subscribe. Bye for now.